Alright, this is online class 15. We're going to start chapter 8 today. I don't intend to do any examples. I'm going to wait for our next face-to-face class to do that. This is a somewhat complicated part of the course, so I want to be sure to work out examples in our face-to-face class, at least at first. And so basically today we're going to work out a introduction. Hang on, I get some trouble here. Okay. Hang on. Alright. Work out or flesh out an introduction of this chapter 8 entitled Hypothesis Testing. Alright. First of all, I want to talk about what an hypothesis is. A hypothesis, well, it's going to be some sort of claim. And in the context of this course is going to be a claim about a population. Whether it's a claim about the population proportion, whether it's a claim about a population mean, whether it's a claim about a population standard deviation, all these things are covered and we will cover in chapter 8. Alright, let me introduce this concept of hypothesis testing by looking at a population. And let's say we're interested in the population proportion of males in this population of persons. All right? Population proportion of males. Let me see if we can get this all on the same screen. And we're going to denote that with lowercase p, and the historical value, or the assumed value of proportion of males in adult U.S. human population is about a half. Okay? Now I want you to consider this. Suppose a researcher makes a claim that based on sample data that the population, the true population proportion of males is greater than one half. Somebody makes that contesting claim. Alright, so the idea here is this hypothesis, this claim, is going to challenge the old assumed hypothesis that males make up half of the population. Right. Suppose further he backs up this claim with the following sample data. Let's say he comes up with takes a sample, an unbiased representative sample, and in that sample he gets a sample proportion of 0.7. Remember, p hat, you recall from chapter 6, or chapter 7 I should say, p hat represents a sample proportion, our notation for sample proportion. Alright, so clearly the sample proportion is more than the assumed historical claim that p is 0.5. Now, I'm going to ask, is this data significant enough to reject the original claim? And that question is the crux of what we will be studying in chapter 8. Remember, the original claim was that little p was equal to 0.5. Alright, so let me cite that profound question again. Do we reject the original claim, based on this sample data? Or do we fail to reject? And those phrases are going to become more familiar to us. Or do we fail to reject the original claim based on our sample data? Alright, the real crux of the matter here is, we have to decide at what point does our sample data become statistically significant. Let me write that down. At what point, at what level of numerical value do we claim the sample proportion is statistically significant? Whoops, sorry, I'm going to erase this. Statistically significant. Regarding difference from the original claim, or the original hypothesis. Okay? So, looking back, at what point do we say this sample data figure is significant? 0.6, is 0.6 enough? 0.7, 0.8, 0.9, 0.99? Where do we draw the line in rejecting or failing to reject the original claim? Write that down. So this is going to be our goal, our major goal in this chapter, to determine the point at which we either reject or fail to reject the original claim. Okay? Alright. We've got to get some notation and some definitions down before we go on. Make a note here. Notation and definitions. Well, we already talked about hypothesis, and some branches of sciences call this an educated guess. Not really. In this context, for this course, it's a claim, any claim, about some property, any property really, of a population. For the purposes of this course, we're going to talk about population proportions, or hypotheses about population proportions, population means, population SDs, and I think for a first course in statistics, that's pretty much it. All right. And hypothesis test, which is what we're learning how to do in this chapter, is a procedure for testing a claim about a population. Okay, now some notation. H sub 0. This is referred to as the null hypothesis. Alright, that's analogous to the original or the historically accepted claim about whatever you're interested in testing, the population mean or population proportion, etc. H0, by convention, is always stated as an equality. What do I mean by that? For example, if somebody's making a claim or wants to test a claim about a population mean, H0 would be stated as P equals something. Right? So here the claim is that the population proportion is 1/2. Okay, H0 is always an equality. Right? Either P equals or mu equals or sigma equals, something along those lines. Okay? H1 is referred to as the alternative hypothesis. And it's kind of like the challenger. H0 is like the king of the hill. H1 is the challenger. It's the new claim. That's challenging the old claim. And by convention, this is always stated as inequality. Either a greater than statement or a less than statement or a not equal to statement. For example, if the original claim is the null claim is that H0 states that P equals 0.5, H1 might say something like this. Either little p is greater than 0.5 or little p is less than 0.5 or little p is not equal to 0.5. Okay? Alright, so we've always got a null hypothesis and an alternative hypothesis, and usually in the beginning of a hypothesis test they're listed together. Alright, so H0 would look something like this, and listed right under it would be H1, which would be one of these three statements, right? P is greater than something, P is less than something, P is not equal to something. Alright, so that's the basic structure of how hypothesis tests are denoted. Let's talk about our test statistic. Well, first thing about test statistic, it's determined by sample data. Right. Typically, it's either a z-score or a t-score. Now, in section 8.3, which is the first section we're going to be performing hypothesis tests in section 8.3, this test statistic is the z-score of a sample proportion. Now that changes from section to section, but since in 8.3 we're going to be testing hypotheses about population proportions, our test statistic is going to be the z-score of sample proportions. Yeah. Again, in 8.3, that z-score would be computed according to this formula, which should look somewhat familiar. P hat is a sample proportion. P is your population proportion, which is assumed to be known until otherwise proven, divided by root PQ over N, where of course Q is the probability complement of your population proportion, and N is your sample size. Again, as before, calculator computes this upstream. Alright, so we won't be bothered with the nuisance of computing z-scores by hand. We'll use the calculator facilities to make that a bit less cumbersome for us. In wide strokes, let me say this. If your sample data, if your test statistic, let me say this. Let me get a new screen. Hang on a minute. if your test statistic, which of course is based on your sample data, is extreme, then the z-score will be, let's say, high or low, depending on what type of test you're running, and might suggest that H0, your original claim, is a false claim. Now, the key word here is suggest. You never really prove or disprove H0. Basically, your sample data might suggest with certain probability that H0 is false. Alright, enter in the concept of p-value. Now, the book's got a formal definition of p-value that I suppose we've got to talk about a little bit. It's the probability of getting a test statistic or sample data at least as extreme as the one from sample data. Alright, that's a very flowery and formal definition. The idea here is this. Z-scores, of course, are normally distributed. Well, that's by definition the standard normal distribution, right? If you've got some sample data that lands you with a z-score, let's say it's here somewhere, I'll call that my test statistic. I claim this extreme area determined by the test statistic is my p-value. Now, this is for what they call a right-tailed test, but again, for our first example, I don't want to get, or for our first introduction, I don't want to get too complicated here. We'll talk about the different type of tests in a minute. Alright, your p-value is very important in hypothesis tests. Our p-value will determine whether we, write this down, whether we reject the original claim or fail to reject the original claim. Okay. If we reject H0, we're implying this. Sample data is strong or statistically significant in suggesting H0 is false. And let me put this down. This is statistically significant. Your sample data, significant. Your sample data is showing a statistical significance in differing from the original claim, H0, right? Alright. If we fail to reject H0, we claim then the sample data is weak. In suggesting H0 is false. In other words, this suggests that H0 is actually true. And in this case, of course, this shows that the sample data is not statistically significant. Okay. Alright, p-value is going to be the king. P-value decides whether we reject or fail to reject H0. And as you might expect, the calculator computes this for us once we enter in our raw data. So again, a lot of the drudgery is eliminated by using the TI-83 or 84 calculator. In wide strokes, we'll say this. Small p-values suggest, and the key word here is suggest, the original claim is false. Remember, the p-value is the tail area, the extreme tail area determined by your test statistic. If this p-value is small, that means this tail area is small, and my test statistic must then be in extreme ranges. How extreme? Well, extreme enough to question the null hypothesis, right? So small p-values suggest H0 is false, and conversely, large p-values suggest H0 is true. In other words, there was nothing wrong with the original hypothesis, and that the new data has failed in its quest to bring down H0. Alright, when I say small p-values and large p-values, the next question that should come into your mind is how small or how large. Alright, what we're going to do is once the calculator compares or calculates our p-value, we will then compare the p-value to this alpha. Alright, so to decide, we will compare p-values to alpha. Now, alpha, we've talked about a little bit so far, is formerly known as our significance level. And here's how we decide. If your p-value is less than alpha, well, remember, small p-values suggest H0 is false. How small? Smaller than alpha. Right? If p-value is smaller than alpha, our conclusion will be to reject H0. Again, this doesn't really prove H0 is false. It suggests, our sample data suggests H0 is false. And conversely, if your p-value is greater than alpha, well, that implies our data is weak and we fail to reject H0. Alright, so in these hypothesis tests, your conclusion will be one of these two statements, either to reject H0 or fail to reject H0 based on comparison to your significance level. Now, the significance level is typically given to you in the problem statement. It will say test the following hypothesis at the 0.05 significance level, etc. Alright? So let me write this down. Significance level is typically given to you in the context of the problem statement. Alright, one thing I want to talk about, one more thing in our introduction to hypothesis tests, are the types of hypothesis tests. Basically, we've got three types. And I'll start out with one of this type? Well, let's see. Let's say, and I'm not even going to specify. Whoops. You got trouble here. Let me get a new screen. Alright, here we go. Types of hypothesis tests. Basically, there's three types. Right? Let's say we're talking about a population proportion, and somebody makes a claim that the population proportion is equal to some value of interest. I'm not even going to specify. And then somebody else says, well, I don't like that claim. I'm going to challenge that claim with this claim. I'm going to claim that the population proportion is greater than some value. Right? If this is the structure of our hypothesis test, I call this a right-tailed test, because I'm going to reject H0 if my sample data yields a test statistic in the extreme right range. Okay, extreme high range. So I call that a right-tailed test. Somewhat similarly, let's say someone makes a claim about a population proportion, and someone challenges that claim with a claim that says the population proportion is less than that particular value. Well, then I will call this a left-tailed test. And I will reject H0 if my test statistic is in the extreme low or extreme left range. And there's a third type of hypothesis test, which we call a two-tailed test. Let's say someone makes a claim that a population proportion equals some value of interest, and then someone comes along and says, no, I don't believe that. Based on my sample data, I claim the population proportion is away from that assumed value, either high or low. All right. In this case, we call this a two-tailed hypothesis test. And in this case, we will reject H0 if test data is extreme high or low. Let me write that down. We will reject H0 if the test statistic is extreme high or low. Alright. Alright. Alright, we're reaching the 30-minute point, so I'm going to call it a day here. I just wanted to lay some groundwork down, some terminology, and some wide-stroke discussion regarding hypothesis testing, basically an introduction to hypothesis testing today. And I will continue with specific examples. And our face-to-face class, which will be the Monday of our return. That'll be Monday, November 26, 2012. This will be a very important class. Really forms the foundation of what we're going to be doing for the last 3 weeks of class. So please be there on time, ready to go on Monday. Alright, that is all for today.